Welcome to the video on chapter 2.3 on carbohydrates and lipids. Okay, so to really understand what's going on with carbohydrates, let's take a look at the word carbohydrate. Okay, hydrate meaning water, H2O, and carbo meaning carbon. So what we can see here from just breaking apart that word is that for every one carbon, there are two hydrogens and one oxygen. And that's if we are building what's called a monosaccharide. Okay, so the ratio for a monosaccharide is 1 to 2 to 1 of carbon, hydrogen, and oxygen. So maybe let's back up for just a second. Okay, this word saccharide means sugar. So sugars are one of the ways that we can say carbohydrate. So saccharide meaning sugar, mono meaning one. Okay, see, these are our simple sugars. Okay, carbohydrates made out of one sugar, and they have a 1 to 2 to 1 ratio of carbon, hydrogen, and oxygen. So some examples there are things I'm sure you've heard of: glucose, ribose, deoxyribose, part of DNA, fructose, and galactose. They're all going to have some kind of a ring shape unless they're dissolved in water, but that's a whole nother situation. But a ring shape, and they can be 5-sided, 6-sided, okay, all with the 1 to 2 to 1 ratio. Disaccharides, on the other hand, are a little bit different. Again, saccharide meaning sugar, di meaning two. So these are molecules that are formed between two monosaccharides. So remember, condensation reactions are the reactions that we use to connect monosaccharides together. Okay, so some examples of disaccharides include maltose, lactose, and sucrose. We'll talk more about those later. Okay, and in the meantime, you're going to need a diagram of a condensation reaction between two monosaccharides. In the past, you've probably drawn the condensation of glucose and glucose into maltose. That's fine if you want to redraw that. Here I have glucose and fructose, a 5-sided sugar, okay, going through a condensation reaction to form sucrose, a disaccharide. So notice here that they're sharing an oxygen. Again, that's called a glycosidic bond. Okay, and I'm asking you to think about, what is this diagram missing? So here we have circled the elements that are removed so that this carbon and this carbon can share this oxygen. Okay, we see that sharing going on right here. Okay, so what am I removing? Well, 2 hydrogens and an oxygen. That's H2O. Well, I need to write that in my diagram. So this condensation reaction between glucose and fructose yields sucrose plus a molecule of water. So these are the disaccharides that you absolutely need to know. Okay, first we need to know is maltose. Maltose is made from 2 glucose subunits, and the source is hydrolyzed starch. So when you eat something with starch in it, like a potato or pasta or anything like that, you've got this long starch chain going through your digestive system, and you have an enzyme called amylase, more on that in a later chapter, that breaks that starch up. Okay, so starch, as we're going to find later, okay, is made by connecting lots of glucoses together. When we hydrolyze that or split it, okay, it's going to split into molecules of maltose. So maltose are our disaccharides. Lactose is, of course, from the milk of mammals. All mammals have lactose in their milk. They don't all have the same amount of lactose, but they all have it in there. Okay, and lactose is made from glucose and galactose, so 2 monosaccharides. And then finally we have sucrose, which I'm sure you've heard of before. Sucrose comes from plants. It's what makes them sweet. And that's made from glucose and fructose, which we just looked at earlier. Notice that all of these end in OSE. Okay, OSE is a very indicative ending of both disaccharides and monosaccharides. Because life's not fair, we don't use that ending for polysaccharides. That would just be too easy, okay? But to identify mono and disaccharides, definitely be on the lookout for that OSE ending. All right, so let's talk about polysaccharides for a minute. Again, here we are, saccharide, sugar, poly meaning many. So we're talking about hooking many sugars up together. We're going to focus on three very important polysaccharides: cellulose, starch, and glycogen. You're going to hear about these, I don't know, about a jillion times throughout the course of taking IB Bio, so you might as well commit them to memory now. Okay, all of them are made from glucose monomers. So they are all chains of glucose, and we can see that here. All these little red dots represent glucose. So what makes them different? Well, the difference comes from the way that they're connected and their shape. And we know shape determines function. So cellulose comes from plants, so it's a plant source, and it's used to construct plant cell walls. So if you're asked to state the composition of plant cell walls, you will, because you're amazing, say cellulose. Okay? And cellulose has a linear shape, so it looks like this. Okay, assuming that you know, and you definitely don't want me to draw this, that when I do that, all of those little tiny, all these chains are actually made up of glucose monomers hooked together, but they are linear. Okay, cellulose has a linear shape. Good Lord, that's terrible. Just look at the picture down here, okay? A linear or line shape. All right, starch also comes from plants, so the source there is plants, and this is how plants store their extra glucose molecules. Plants are amazing and awesome, and they're using photosynthesis to create glucose all the time. When they have extra glucose, they want to put it in the bank. And the way they store that extra energy, okay, is via starch production. Okay, so starch is going to be a spiral shape. So something like this. Okay, so we have something linear, we have a spiral. Again, don't forget that this spiral is actually a bunch of glucose molecules hooked together. I hope you're getting the gist of what's happening here. So here it is in a spiral form. And then we have glycogen. Glycogen comes from animals. It's an animal-sourced polysaccharide. And this is how animals store their extra glucose. So I was just behaving poorly and eating some ice cream before I made this video. And now, since I'm sitting on my backside, my body isn't using that glucose right away. So what's happening is that glucose is being stored as glycogen. Now, we're going to learn later that this involves your pancreas and your liver and some cool hormones, okay? But for now, you just need to know that it gets stored as glycogen. And that is a branched shape. So you're going to want to draw that. It's actually really cool. It branches and it kind of forms this spiral shape. So, wow, this is looking really bad. But if you can imagine kind of like a Christmas wreath, okay, kind of is formed by branches, and then you can turn those branches into a spiral shape. Oh wow, look at that. Look how good my drawing just became. Great. In class, we're going to take a look at some of this molecular visualization software so that you can see what these really look like in 3 dimensions, and so that this is the last time, thank God, you have to deal with my horrible drawings. Okay, so I want to start off then on our discussion with fatty acids with another horrible drawing. This I'm going to try to make a little less horrible. Remember, to draw a fatty acid, we're going to start with a carboxyl group on one end. So carboxyl is COOH, one of the O's is double bonded. A methyl group on the other end. Methyl is CH3. And then in the middle, you have a carbon group, and there can be a whole number of these things. So anywhere from 11 to 23 of these guys in the middle, sandwiched between a methyl and a carboxyl group. Okay, so just for your information, here's how we're going to talk about fatty acids, okay? Fatty acids can either be saturated or unsaturated. Then we can further categorize unsaturated as polyunsaturated or monounsaturated. And polyunsaturated can be further broken down into cis and trans. So I'm not asking you in your notes to write this, but if this kind of helps you to understand what we're talking about, by all means, it's a good idea to kind of find somewhere to jot that down. Okay, so let's talk about saturated fatty acids first. Okay, why? Because they taste delicious. Saturated fatty acids have all single bonds in between their carbon atoms in the middle. So remember, I just drew that middle carbon atom group looking like this with a big N on the end. Okay, this one would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 of those. Okay, and if all of them are single bonded together, that means carbon's other bonds are going to be taken up by hydrogens, okay? So it's said to be saturated because all of the carbons are carrying as many hydrogen atoms as they can. And I tend to think of this as a parking lot. So here all the parking spots are filled by hydrogen atoms. These come from animals, okay, whether it be from tissue like in the meat or from dairy products or eggs, and they are solid at room temperature. So if you set cheese or butter or meat fat out on the counter for hours and hours and hours, that fat will remain a solid. Monounsaturated fats are exactly what they sound like. Love it when that happens. Mono meaning one, un meaning not, and then saturated. So these are not saturated fats, and they're not saturated because they have one empty parking spot. Okay, so what's that going to look like here? Well, they have an empty parking spot when there's a double bond somewhere in the chain. So whereas saturated fatty acids have all single bonds, unsaturated fatty acids have a double bond somewhere. And we know that carbon can only form 4 bonds. So here they are, 1, 2, 3, 4. That means there's no room for a hydrogen atom down here anywhere. So that parking spot is going to be empty. And what happens when you have an empty parking spot is we get a bend. That's because these two hydrogens, they actually really don't like each other. These guys are always like unfriendly and very nasty. They repel each other. Unfortunately for these guys, these two hate each other just as much as those two, so the repelling forces kind of equal out. Well, here, these two guys hate each other, so they try to repel each other, and there's no hydrogens down here to stop it. So we end up getting this bend in a fatty acid chain. And these can sometimes come from plants or animals. It's just kind of depending. When I'm seeing animals, I'm thinking like particularly of fish. Okay, but a lot of plants have these also. And they are liquid at room temperature. Polyunsaturated fats, again, poly meaning many, have many or more than two or more double bonds somewhere in their chain. They always come from plants, and they are liquid at room temperature. So everywhere that there's a double bond, we get a bend in our chain. Okay, so whereas saturated fatty acids are straight, monounsaturated fatty acids have one bend in them because there's one double bond. When we have multiple double bonds, we get a very bendy shape. Yes, bendy, a technical term. Now, Fats are very interesting because we can synthetically manipulate them. So we're so awesome as humans that we're able to take naturally occurring fats and do unnatural things to them for our own good purposes, I suppose. So trans fatty acids, a cool story, first came about because fast food restaurants noticed that their cooking oil was going bad pretty quickly. Like it was only lasting, a day or so, and then they would have to replace it. And every time you have to replace it, that costs money. So we know that oils are unsaturated fats. They're liquid at room temperature. They've got all these double bonds. Well, these clever fellows figured out that they could hydrogenate these fats. In other words, they could add hydrogens in to where they were previously missing. And what that does is it kind of straightens out that chain and it makes them last longer. Okay, so a lot of the things that are kind of like synthetically created come from these hydrogenated fats, and they're a lot less healthy for you. They tend to result in higher bad cholesterol and some other problems. And again, they're synthetically made by adding in those hydrogens. They are much, much different than cis fats, okay? So trans fats are polyunsaturated fats that have been fully or partially hydrogenated. They're not natural. They're not healthy, okay? And if you take a look at what's going on down here on the bottom, you'll see that when we hydrogenate things and when we add hydrogen atoms, what it does is it straightens out that fatty acid chain to where it most closely resembles a saturated fat, which is also not good for you. Okay, so as before we had a cis fatty acid. When we hydrogenate them, they turn into trans fatty acids, which more closely resemble a saturated fat. Okay, so they're not healthy for you. Cis fats, on the other hand, are polyunsaturated fats that are naturally curved, and this includes things you may have heard of before, like the omega-3 fatty acids. Okay, that's only named because of where the double bond is. You don't have to worry about that. These are good for you. They're found in fish. They're found in some nut products. And for those of you who are wondering how we get these names, cis and trans, it comes from the relationship of hydrogen atoms on the fatty acid chain. Okay, so cis and trans, those words tell us a lot, right? So trans means across. So the hydrogen atoms that we add in are across from each other. That means this one and this one repel each other with equal strength as this one and this one. So if those repelling forces are the same, it's going to straighten out my chain. Cis, on the other hand, has the hydrogen atoms on the same side. This is naturally occurring. So what's happening is that these molecules are repelling each other and there are no hydrogens down here to stop that. So it bends the chain. And that's how we get the names cis and trans. So when you're looking at a nutrition label, I don't know, does anybody do that? I'm not sure. Anywho, if you ever look at a nutrition label, which I suppose you should, you have to consider a couple of things, right? So first of all, you should be considering the total amount of fat, okay? Fat has more calories per gram than other types of nutrients. There are 9 calories per gram in a molecule of fat or a gram of fat, whereas carbs and proteins have 4 calories per gram. Okay, so there's a lot more calories in fat, and increasing your caloric intake or your overall fat intake can be bad for you. Even if you're eating good fats like omega-3 fats, you're eating your weight in salmon and avocados, you're still ingesting a lot of fat, okay? And you have to watch the total amount. You also need to pay attention to the type of fat. So saturated and trans fats are listed here. They're not as healthy for you as cis polyunsaturated fats. So you really need to consider both the total amount and the type of fat when you're determining what makes the food healthy or not. And of course, There are a ton of other things, I shouldn't be telling you this, that we should consider in terms of evaluating food for its health benefits. But since we're only talking about fats here, I shouldn't digress too far. Okay, make sure that you're looking at the total amount and the type. All right, now I keep saying fats. Fats is like the lazy person's way of describing what we should be calling a lipid, okay? And lipids are the result of a condensation reaction, so we're putting things together between glycerol and 3 fatty acids. So that's where we get this word triglyceride. Tri meaning 3, glyceride referring to glycerol, okay? So that's where we're getting this word triglyceride. And you're going to need to draw what this condensation reaction looks like. So again, you need kind of a before and after picture. And here's the before picture. I wouldn't draw these blue circles. These are just here to show you where the water is coming from. If you want to draw them, that's okay, because I know you're not listening to me anyways. Okay, so here's our glycerol molecule. If it were me, I would label that as glycerol, because you know at some point I'm going to show you a picture of just glycerol and ask you what that is, and you don't want to panic. Okay, so here's glycerol. It's carbons, okay, with 3 OH groups, and then the rest of the bonds are filled with hydrogen. Here are my generalized fatty acids. Okay, so notice this has been flipped around from the way that I drew it yesterday or earlier, and that's okay. Molecules are allowed to move. We've got the carboxyl group on one end, the methyl group on the other end, and then a bunch of those CH groups. These would all be saturated fatty acids, all single bonds, just an FYI. Okay, so once 3 of those line up next to the 3 OH groups, what's going to happen is the OH, okay, from the carboxyl group is going to combine with the H from the OH group over here to make water, H2O. Okay, H2O, H2O. So that when they join, when they bond, they're going to be sharing this oxygen. So now in the after picture, the carbon from the glycerol and the carbon from the carboxyl group of our fatty acid are sharing this oxygen, okay? And that, of course, removes 1, 2, 3 molecules of water. So we need to note that. Whether or not you choose to write the word enzymes there is fine. Of course, with any biological reaction, this involves enzymes, but it doesn't really have anything to do with your understanding of a condensation reaction. This, however, is super duper important. Okay, so why are we eating these yummy foods in the first place? Well, because we need energy. Now, our cells are kind of like annoying car washes. When you go to the car wash and all it takes is like strange tokens and you have to dig around for all your cash that you never have on hand and put them in the change machine for these strange car wash tokens. Well, that's kind of what's going on with your cells. Your cells can only use this strange token called ATP. All the cellular processes rely on ATP. The food you eat doesn't have ATP, okay? It has things like glucose and other stuff, okay? The energy in that food is used to generate ATP, just like your dollars are used to get car wash tokens, okay? Now, if your body already has a sufficient amount of ATP, your body's not stupid. It's going to store that energy, okay? How is it going to store that energy? Well, it's going to do one of two things. It's going to turn that extra glucose energy into glycogen, or it's going to turn it into triglycerides. Okay, so just to recap, the energy in your food, I'm talking about glucose. We use glucose to generate ATP. If we're already good on ATP and we don't need any more, we're going to have a lot of extra glucose molecules. We're either going to connect a bunch of them together to make glycogen, and that is stored in liver and muscle tissue, Or we're going to do some cool magic tricks and store that extra energy as triglycerides in our fat cells. And of course, humans have annoyingly evolved to store our extra energy as fat, okay? So I say that's annoying because come Monday, I'm gonna have to figure out how to put on my pants, okay? But really, in terms of physiologically speaking, storing extra energy as lipids has a ridiculous advantage over storing them as carbohydrates. So first of all, they have twice the energy content, okay? So if I store something as a lipid and then I turn it in, I can generate twice as much ATP, okay? So lipids are very energy dense. And the second thing is that they're not soluble in water. Lipids are non-polar. They don't dissolve in water. So they don't mess up the osmotic balance of your cells. If it dissolves in water like carbohydrates and it was all dissolved in your blood plasma or in your cells, water would be either entering or leaving your cells and causing you all kinds of crazy problems. Okay, imagine all of your blood cells shriveling every time you ate an ice cream cone just because there's extra glucose in your blood. That would suck. Okay, so our bodies store them as lipids. Now, storing them as lipids is okay. It is okay to have fat in your body, okay? You're gonna have fat in a lot of places. Of course, underneath of your skin for thermal insulation, so that's good. And then you're also going to have it surrounding your organs because your organs are smushy and sensitive, which is a bad combination, okay? And they need something to protect them, and fat does a pretty good job of that. Okay, so it is okay to have some fat in your body. However, if you start to accumulate extra fat, okay, that extra fat can cause some really bad problems. High cholesterol, heart attacks, stroke, okay, and maybe like the worst one, death, okay? So we can use BMI or body mass index to kind of give us an idea of are we at a healthy weight range for our height, or are we accumulating too much extra weight in the form of fat and causing some kind of a decreased lifespan, okay? So the higher our BMI is, okay, the more years we're losing off of our average lifespan, which is pretty crazy here. Now, BMI takes into account, again, your height and weight, okay? So someone that weighs 150 pounds could either be grossly overweight or grossly underweight, depending on their height. There are 3 ways to calculate BMI. The easiest one is to use an online calculator, and because that's the easiest one, you know you'll never be asked to do that in an IB class. Okay, you're gonna have to do it the hard way. So the hard way is probably by calculating it with a formula. I would probably write this formula down because chances are I'm gonna make you do this at some point. Okay, and that's you're gonna take your weight in kilograms divided by your height squared, and that height should be in meters. Okay. A popular test question in terms of IB test uses these things called nomograms to calculate BMI, and they look like this. Don't panic, this is not as bad as it sounds. Okay, so let's, for instance, take someone's BMI. Let's say that I have a female who weighs 150 pounds, okay? And, well, that's really stupid. I don't know why I did that because we're going to be using the metric system. So I don't know. Let's say she weighs 75 kilograms. Okay, and in terms of centimeters, let's say that she is 180 centimeters tall. I can either use that information to calculate the BMI in this formula, or I can use a nomogram. To do that, I'm going to draw a line that connects my 2 values. So I would find 75 kilograms on this chart, which is right here, and I would find 180 centimeters, which is right here, and I would use a ruler, which I don't have, to draw a line between them. Okay. Now, wherever this line crosses the woman category, because she's a female, will give me her BMI range, okay? So she's going to be in the overweight range, okay? That's not true. I'm an idiot. She's not overweight. Why isn't someone correcting me here? She's in this acceptable range, okay? And that's because this line crosses right about here. Okay, so I can actually calculate her BMI. Her BMI looks to be about 21, okay? And that is in the acceptable range. Okay, whew, glad that's over. So how do we interpret BMI? Okay, so let's say I don't have a nomogram. Let's say I just use that formula to calculate someone's BMI, and they had a BMI of 28.6. Oh, okay, what does that mean? Well, a BMI of 28.6 would fall in this category of being overweight, okay? So underweight, normal weight, overweight, and obese are kind of our categories. So here we have this like strangely asexual man to kind of show you what those different categories look like, okay? Obviously, with these categories being not healthy, and underweight isn't healthy either. Now, we have to be careful because there are times when someone can weigh a lot in comparison to their height, and it gives them a very high BMI. If that person's weight is due to muscle mass, then that carries a lot fewer health risks. So it says they have a BMI, but they probably won't have the typical health risks of like heart attack and death and all that annoying stuff, as someone who has a BMI of the same number, but whose weight is largely due to fat. So that's just kind of an FYI there. And speaking of fat, time to go get some more ice cream. And that ends our video on chapter 2.3 on carbs and lipids.